Welcome back to Numerical Analysis. It's Friday, April 18th, and we're going to talk about higher order and adaptive methods for systems of ordinary differential equations. But first, a little housekeeping kind of update. I had intended to get a video out explaining options for the final, which will be optional. Still haven't done that. As I said in my last video, I'll be working on grading and catching up with that kind of stuff this weekend, and I'll get that video out this weekend. So, again, by the beginning of the week, you will know where you stand in the class, and you can make a decision as to whether you want to just take the grade you currently have or to try to improve it by taking a final exam. So in the meantime, let's look at probably our last major topic for the semester. What we're going to do here is put together some ideas we saw from Euler's method for a single differential equation and the sort of higher order ideas and the adaptive step size ideas, and we're going to apply those to a system of ordinary differential equations. And just a couple of basic ideas here are going to transfer over very nicely from the 1DE case to the system case. First, we'll use higher order Taylor approximations at each step to project the solution forward. And then, as we saw in the single ODE case, we can use the highest degree term in the Taylor polynomial to estimate the approximation error. And from that, we can choose a step size that makes sure that our estimated error remains within prescribed bounds. So let's recall Airy's equation and the system that corresponds to it. Airy's equation is a order 2 ordinary differential equation, and when you translate that to a system of first order equations, you get this system you see here: dx dt equals y and dy dt equals t times x. So this is a system for two unknown functions x and y, and we went through the basic Euler's method for this system in our last discussion. What we want to do now, though, is try to kick it up a notch by, instead of using first degree Taylor polynomials, use higher degree Taylor polynomials in making the projections forward for each step. So let's begin by looking at the degree 2 Taylor polynomials for the unknown functions x and y, and let's center them at some current time value that we've arrived at in our solution process, say t equals t sub n. So here I'm just writing the generic form of the Taylor polynomial of degree 2 for x and the Taylor polynomial of degree 2 for y, both centered at t equal t sub n. So in order to figure out what these polynomials are, we need to know the values of the 0th, first, and second derivatives for both x and y. Now, of course, the differential equation gives us the first derivatives right here. So we'll be able to use that. The solution process will give us the values for the 0th derivative from the previous step. So all we really need to do to extend the method to second degree is to look at the second derivatives of the solutions x and y. So we do that in a way that should be familiar to us by now. We can take the original ODE and use it to work out what higher order derivatives of x and y would be. So for instance, for the second derivative of x, well, that's obviously the derivative of the first derivative. But from the ODE itself, we know that the first derivative is equal to y, the first derivative of x, that is. So dx dt is y, and then we were looking at the derivative of y. But the derivative of y, again from the ODE, is t times x. So this tells us that the second derivative of x is t times x. Similarly, we can compute the second derivative of y, and you see that worked out here. It's the derivative of the first derivative. From the ODE, we know that the derivative of y is t times x. When we take the derivative of this, we have to remember that both t and x are functions of t, so we actually have to use the product rule here. So the derivative of t times x with respect to t is the derivative of t, which is 1 times x, plus t times the derivative of x. And then from the ODE, we know that the derivative of x is y again. So we get the second derivative of y with respect to t is x plus ty. So in summary, from the original system, we're able to derive the second derivatives of the unknown solutions x and y in this way, and there you see them. Okay, so how do we use this to construct Taylor polynomials? Well, think about Euler's process. At a given stage, I'm calling, let's say, stage n, you've got a current time value, a current solution value, xn, and a current solution value for y, yn. Now remember, xn means the solution x evaluated at time t sub n, the current time. So x of t sub n would just be xn. X prime of t sub n would be what? Well, we know that x prime is equal to y, so at time tn, x prime of t sub n would just be y evaluated at time t sub n, or y sub n. And what about x double prime of tn? Well, from our previous work, x double prime is t times x. And so x double prime when t is equal to tn would be tn times xn. And so we have that. And that's our second degree Taylor polynomial for x centered at t equals t sub n, the current time step. Similarly, you can derive the second degree polynomial for y, and I'm calling that q here. Y prime at tn, well, from the original DE, y prime is t times x, so y prime at tn would be tn times xn. Y double prime at tn, from our work a few slides back, would be x plus ty evaluated when t equals tn. So that would be xn plus tn times yn. And there we have the second degree Taylor polynomial for y. So now we have, I'm calling them local degree 2 approximations for x, and that would be p2, and y, and that would be q2. They're local because they're centered, they're most accurate right at the current time step, which is, we're calling tn here. Okay, so that's how we get a higher order approximation working for us. The second component we saw was adaptive step size. The basic idea we saw there from our study of just a one-dimensional differential equation was that you can use the highest degree term in the local Taylor polynomial as the error estimate. And then how do you take advantage of that by setting a single step error tolerance, which we're calling tau, and then we choose our time step, which is just that increment between the next time t and the current time tn, so that the estimated error in absolute value is less than that error tolerance. Now, the additional wrinkle here is that we've got two components of the solution, x and y. So each of those will have its separate error estimate, and we'll get a separate time step for each of those. So I'm calling delta t1 the time step that we will derive for x, and delta t2 the time step for y. But in projecting forward, we need to project both x and y forward the same amount. In other words, we need to use the same time step in projecting both x and y. So to ensure that that time step stays within the error tolerance for both x and y, our time step would be the minimum of the time steps you get from x and y. Okay, so let's see how this goes in an example. We'll consider the same initial value problem we did previously, that is the Airy system with an initial time of t equals -3, and at that time x is 1 and y is -1. So that's our initial value problem. Let's use an order 2 adaptive Euler method with a tolerance of tau is 10 to the -3rd to compute an approximate solution. So again, the keys here will be in that local Taylor approximation for x, which I'm calling P2, and for y, which I'm calling Q2. And then just remember what we do at each step. First, we determine what P2 and Q2 look like for the current step. We compute the step size we need to take that'll keep us within our error bound, and then we project the solution forward. So step 0, as usual, is to gather our initial conditions. Again, the initial time was -3, and at that time, x was 1 and y was -1. So that gives us our initial values, t0, x0, and y0. Ready to move to step 1. So let's first compute our Taylor polynomials, P2 and Q2. So what I'm using here is just my most recently computed values for t, x, and y, namely t0, x0, and y0, and I'm plugging those in to my Taylor polynomial for p. So this is x0 now, y0, and t0, and I'm plugging those in here, and that's how I get that polynomial for p, which I'm not simplifying again, so you can hopefully see where everything's coming from. Do the same thing for q. You get the local polynomial for y at this step. Then your error estimate for x is that highest degree term in the Taylor polynomial. So there it is right there. That's my error estimate. And I'm just going to call t minus the current time value delta t, just to save with notation. So working that out, the error estimate for x is -3/2 delta t squared. The error estimate for y, similarly, is that highest degree term in the Taylor polynomial for y. So it's this guy here. And I'm going to go ahead and simplify that. 1 plus 3 is 4, divided by 2 is 2. And again, I'm calling t minus the current time value just delta t. So we get 2 delta t squared as our error estimate for y. And then we compute step sizes. The step sizes, remember, we want to choose delta t so that the absolute value of the error is less than our tolerance. And this was our tau, which was 10 to the -3rd. So there's the error estimate for x. And we want that to be an absolute value less than 10 to the -3rd. Just work that out, and you find that delta t, an absolute value, has to be less than 2/3 10 to the -3, all to the 1/2 power. That turns out to be about 0.02582. I'm rounding things to 4 significant places here. In doing the calculations, you don't want to round it all, though, of course. Use the full accuracy of your calculator. So this is saying that any time step that's less than 0.02582 would yield an estimated error in x that's less than 10 to the -3rd. And of course, we want to take the largest time step that satisfies our error requirement. So delta t1, the time step for x, I'll take to be 0.02582. Do the same thing for y. Use the error estimate for y, put it in absolute values, and make it less than your tolerance tau. Solve for delta t, and this time we get 0.02236. So any step size less than that would give an estimated error in y that's less than our error tolerance. And so delta t2, it would be 0.02236, the largest step size I could take for y and keep within the prescribed error tolerance. But I want to simultaneously step x and y forward and stay within the error tolerance. So that means I have to take my simultaneous step size to be the minimum of those two. And that, of course, is the 0.02236. So that's going to be my step size. And then I project the solution forward. So my new time value is the old time value plus the step size. So that's my -3 plus my step size. And there you have it. To project x forward, I plug the new time value into the Taylor polynomial for x. And that's what I'm doing here. And we get this value here. So remember, I'm using there the Taylor polynomial for x that we just generated a few slides back here. And the same thing for y. To project it forward, I would take my new time value and plug it into the Taylor polynomial for y, and that's this guy. And so we get this value here, -1.066 and some change. And now you would repeat this process starting with t1, x1, and I'm sorry, this should be y1 here. That's a typo, my bad. And then you would repeat the process from there. So here is MATLAB's computation of this. This is the adaptive Euler method of order 2 with a tolerance of 10 to the -3. And I've projected the solution forward up to time t equals 2. So the red curve you see here is the solution x, and the blue curve is the solution y. And all the coloring in there is MATLAB showing me the interpolating quadratic now that connects the dots in each of those graphs. This process, you can use order 3 approximations, order 4 and higher, and I thought I would just show you what would happen if you do that. So the next slide, I want to use an order 3 approximation with the same error, and there you see it. So what you see happens is that because we're using now an order 3 approximation instead of an order 2 approximation, we can stay within that error tolerance by taking much larger steps. In fact, I went and looked back at the results of the computations. For the order 2 approximation, it took actually 143 steps to get from t equal -3 to t equal 2 with that local error tolerance of 0.001. But for the order 3 approximation, it only took about 40, actually 38. So in other words, by going from order 2 to order 3, the step size on average increased by a factor of 3. We're able to get the same local accuracy with a lot larger step sizes, and that's because we're using a more accurate Taylor polynomial of order 3 here. We could go ahead and look at what would happen with order 4. You see now the step size has increased even more. Now, instead of the 38 steps it took for order 3, it took only 19 for order 4. So the step size has we're able to increase by a factor of 2 now over order 3. And going one step further to look at an order 5 approximation, you'll see the step size can increase even more. This time it only took 12 steps. There is kind of a law of diminishing returns here. As you increase the order more and more, you're not going to just have you're not going to be able to double the step size every time you increase an order or anything like that. So there would come a point at which you've got sort of the law of diminishing returns kicking in. But as we see, the process is fairly straightforward, and depending on the problem, it could be advantageous to use an order 3, 4, or 5 approximation. You could ultimately get an accurate solution with much less computation than an order 1 approach would take. So there you have it. Euler's method with higher order Taylor approximations at each step, and with adaptive step size working for us at each step, so we can take the biggest step possible and stay within an error tolerance. And all of this applied to a system of ordinary differential equations. So I think you can see the power of numerical methods in elucidating what the solutions are doing in a system like that doesn't have an elementary solution that you can just sort of calculate directly. Okay, well, that's it for now. Again, I will be back in touch early next week with updates on our end of semester plans. In the meantime, there will be another homework about applying these higher order methods to systems of equations, so stay on the lookout for that. Hope you all have a good weekend. And as we get ready to move into the last week of class, I hope you are healthy, of good state of mind, and are staying well. So take care, and I'll see you soon.